Good morning, everyone. Welcome to our class on functions. Today, we're going to lay the groundwork for a topic that is absolutely central to mathematics. We'll be starting with the fundamental concept of a function. By the end of today's lecture, you will be able to define what a function is, use proper function notation, and distinguish between different types of functions. These are our main goals for this first part of the lesson. So let's start with the most basic question. What is a function? At its core, a function is a rule. It's a specific type of rule that takes an input, which we usually call x, and maps it to exactly one output. I repeat, for every one input, there is only one possible output. Think of it like a machine. You put something in, the machine follows a rule, and something specific comes out. If you put the same thing in again, you'll get the same thing out every single time. Let's consider a simple rule. Imagine our rule is to square the input value and then add 3. How do we write this using mathematical notation? There are two common ways. The first and most common is f of x equals x squared plus 3. Here, f is the name of our function, x is the input, and x squared plus 3 is the rule that gives us the output. This notation, f of x, was first used by the brilliant Swiss mathematician Leonhard Euler way back in 1750. And it's been the standard ever since. An alternative way to write this is using a mapping notation. This reads as the function f maps x to x squared plus 3. It expresses the same exact idea. The input x is transformed into the output x squared plus 3. Both notations tell us the same thing. For any input x, the function f will square it and add 3 to produce the output. Now let's talk about the different kinds of relationships a function can have between its inputs and outputs. First, we have what's called a one-to-one function. This is a function where every output value is unique and corresponds to only one input value. No two different inputs will ever produce the same output. A classic example is the cubic function. Let's look at the graph of y equals x cubed. Notice how for any y value you pick on the vertical axis, you can only find one x value that produces it. For example, the output 8 only comes from the input 2. The output -27 only comes from the input -3. Each output has exactly one input source. This is the defining characteristic of a one-to-one function. On the other hand, we have many-to-one functions. As the name suggests, this is where it's possible for different inputs to lead to the same output. The most common example of this is the quadratic function. Consider the graph of y equals x squared. Let's pick an output value, say y equals 4. What input or inputs give us 4? Well, 2 squared is 4, but also -2 squared is 4. So two different inputs, x equals 2 and x equals -2, both map to the same single output, y equals 4. As you can see on the graph, a horizontal line can intersect the parabola at 2 points, x1 and x2, which share the same y value. This shows that multiple inputs are mapping to one output, making it a many-to-one function. So to recap, we've defined a function as a rule mapping each input to a single output. We've seen the fx notation, and we've distinguished between one-to-one functions, where each output is unique, and many-to-one functions, where different inputs can share an output. Now that we understand what a function is and how to write it, let's practice using the notation to evaluate functions. Our goal here is simple. Given a function and an input, you'll be able to find the corresponding output. Evaluating a function just means substituting a given number for the input variable x and calculating the result. Let's take a look at this worked example. We are given the function f of x equals 2x plus 7, and we're asked to find f of 3. The notation f of 3 is an instruction. It tells us to take the number 3 and use it as the input for our function f. So everywhere we see an x in our functions rule, we're going to replace it with a 3. This gives us f of 3 equals 2 times 3 plus 7. Now we just do the arithmetic. 2 times 3 is 6, and 6 plus 7 is 13, so f of 3 equals 13. This means that for our function f, an input of 3 produces an output of 13. Let's try another one together. Let's say we have a new function, g of x equals x squared minus 5, and we want to find g of -4. What's the first step? Take a moment to think about it. That's right, we substitute -4 for x. It's very important to use parentheses here to avoid errors, especially with negative numbers. So we write g of -4 equals, in parentheses, -4 squared minus 5. -4 squared is positive 16. Then 16 minus 5 gives us 11. so g of negative 4 is 11. The input 9 of 4 maps to the output 11. Excellent. We've now seen how to take a function defined by a rule and evaluate it for a specific input. This is a fundamental skill we'll use constantly. We've established that a function must map every input to a single output. But how can we quickly tell if a graph represents a function? For this, we have a very simple and powerful graphical tool. By the end of this segment, you'll be able to use what's called the vertical line test. The core idea goes back to our definition. For any given input x, there can only be one output y. If we find even one x value that corresponds to more than one y value, the relation is not a function. This leads us to the vertical line test. It's a visual check. If you can draw any vertical line that crosses the graph in more than one place, it is not a function. If every possible vertical line you can draw only ever hits the graph once, then it is a function. Let's apply this to the examples from our notes. First, look at graph A. Imagine sliding a vertical line like a ruler from left to right across this graph. Notice that no matter where you place the vertical line, it only ever touches the blue curve at a single point. Try it anywhere. Here it touches once, here once, and here once. Since there are no values of x that map to more than one output, this graph passes the vertical line test. Therefore, it represents a function. Now let's look at the second example. Now consider graph B, which is a circle. Let's perform the same test. Can we draw a vertical line that hits the graph more than once? Absolutely. Take a moment to visualize where. If we draw a vertical line, for example at x equals 1, it intersects the circle at two different points, one above the x-axis and one below. This means that the single input x equals 1 is mapped to two different outputs. This violates the definition of a function. Because we found a vertical line that intersects the graph more than once, this graph fails the vertical line test and is not a function. So we now have a reliable visual method, the vertical line test, to quickly determine if a graph represents a function. It's a direct application of the rule that each input can have only one output. All right, let's move on to two incredibly important concepts related to functions, domain and range. Knowing the rule of a function is one thing, but we also need to know what inputs are allowed and what outputs we can expect. Our goals here are to define domain and range, and then to learn how to find the domain of a function, which is often called finding the largest possible or natural domain. Let's start with the domain. The domain of a function is simply the set of all possible input values, or x values, that the function can accept. For many functions, the domain is all real numbers. If a domain isn't specified, we usually assume it's all real numbers for which the function is defined. We can write this as x is an element of the real numbers. However, some operations in mathematics are restricted. There are certain things we just can't do. When finding the domain, we're essentially looking for any values of x that would break the function. There are three main rules to watch out for. First, we can't take the square root of a negative number in the real number system. Second, division by 0 is undefined. And third, we can't take the logarithm of a negative number or 0. We must exclude any x values that would cause these things to happen. Let's see this in action with an example. We need to find the domain of f of x equals the square root of 2 minus x. Which of our three rules applies here? It's the square root rule. The expression inside the square root, which is called the radicand, cannot be negative. In other words, 2 minus x must be greater than or equal to 0. It can be 0 because the square root of 0 is just 0, but it can't be negative. So we set up the inequality. 2 minus x is greater than or equal to 0. Now we solve for x. We can add x to both sides. This gives us 2 is greater than or equal to x, which is the same as saying x is less than or equal to 2. This is our domain. Any number less than or equal to 2 is a valid input. Any number greater than 2 would make the inside of the square root negative, which is not allowed. Let's try an example with our second rule. Consider the function f of x equals 1 over the quantity x minus 2. What's the potential problem here? The problem is division. We can never divide by 0. So we need to find any x values that would make the denominator x minus 2 equal to 0. We set the denominator not equal to 0. X minus 2 is not equal to 0. Adding 2 to both sides, we find that x cannot be 2. The domain is all real numbers except for 2. Any other number is a perfectly valid input. Now that we know how to find the domain, let's briefly define the range. The range is the other side of the coin. It's the set of all possible output values, or y values, that a function can produce. Once you know the allowed inputs, the domain, the range is all the outputs you can get from them. We've now defined domain as the set of allowed inputs and range as the set of possible outputs. And importantly, we've learned the key restrictions to look for when determining a function's domain. We've defined the range as the set of all possible outputs. Finding the range algebraically can sometimes be tricky, so one of the best methods is to start by looking at the graph of the function. Our goal in this segment is to use a function's graph to determine its range. Let's revisit a function we've already worked with, but this time with a specific domain. We need to find the range of f of x equals the square root of 2 minus x, but notice the restriction. The domain is only x values less than or equal to 0. First, let's visualize the graph. We can use a graphing calculator or sketch it by hand. The graph of y equals the square root of 2 minus x starts at the point 2, 0 and curves up and to the left. However, our domain is restricted to x less than or equal to 0. This means we are only interested in the part of the graph on the y-axis and to its left. So, we're only looking at this portion of the curve. Now, to find the range, we need to look at the possible y values for this part of the graph. What is the lowest y value it reaches? The lowest y value occurs at the rightmost point of our allowed domain, which is at x equals 0. Let's find the value of the function at this boundary point. We need to calculate f of 0. Substituting x equals 0 into the function, we get f of 0 equals the square root of 2 minus 0, which is simply the square root of 2. So the point 0 square root of 2 is the lowest point on our restricted graph. As x gets more negative, the value of 2 minus x gets larger, and so does its square root. The graph goes up and up from this point. Therefore, the range, the set of all possible outputs, is all values greater than or equal to the square root of 2. We write this as f of x is greater than or equal to the square root of 2. By sketching the graph and considering the domain, we were able to clearly see the set of all possible output values, which is the range. Let's now introduce a new concept, the inverse of a function. The basic idea of an inverse function is that it reverses or undoes the action of the original function. In this part, we'll aim to understand what an inverse function is and, crucially, why not all functions can have one. Let's think about this undoing process. If a function f takes an input and gives you an output, the inverse function, which we denote with a superscript 9 and 1, takes that output and gives you back the original input. So if f of input equals output, then f inverse of that output gets you back to the original input. For instance, if a function f takes the number 2 and turns it into 4, then its inverse function, f inverse, must take 4 and turn it back into 2. Now, here's the most important point about inverses. Take a moment to think. Can every function be reversed? What might be a problem? The problem arises with many-to-one functions. It is a critical fact that only one-to-one functions have inverse functions. Let's understand why. Remember our many-to-one example, f of x equals x squared. With this function, both an input of 3 and an input of minus 3 produce the same output, 9. Now let's try to create an inverse. If we ask the inverse function, what input gave me 9, what should it answer? Should f inverse of 9 be 3? Or should it be negative 3? It can't be both. Remember the definition of a function. An input can only have one output. The inverse relation would need to map the input 9 to two different outputs, 3 and negative 3. This violates the definition of a function. Because of this ambiguity, a many-to-one function cannot have a well-defined inverse function. The reversal process doesn't work. Only a one-to-one function where every output is unique can be perfectly reversed. One final, but very important note on notation. The superscript -1 here does not mean a reciprocal, like it does with numbers. F inverse of x is not the same as 1 over f of x. This is a common point of confusion, so be very careful. It's a special notation just for inverse functions. To summarize, an inverse function f inverse reverses the action of a function f. And critically, only one-to-one functions have inverses, because the reversal must be unambiguous. Now that we understand the concept of an inverse function, let's learn how to find the value of an inverse function for a particular number. Our goal is to be able to solve problems like find f inverse of 11. The key is to remember what the inverse function does. Finding f inverse of some number, let's call it k, is the same as asking the question, what input x do I need to give to the original function f to get an output of k? So the strategy is simple. To find f inverse of k, we set our original function f of x equal to k, and then we solve that equation for x. The value of x we find is the answer. Let's walk through an example. Suppose we have the function f of x equals 3x plus 5, and we want to find f inverse of 11. Following our strategy, we are looking for the x value that makes f of x equal to 11. So we set up the equation 3x plus 5 equals 11. Now we just need to solve this simple linear equation for x. First, we subtract 5 from both sides. That gives us 3x equals 6. Then we divide both sides by 3, and we find that x equals 2. Since an input of 2 gives an output of 11 for the function f, that means the inverse function must take 11 and give back 2. Therefore, f inverse of 11 is 2. We have found our answer. Let's do one more to solidify the concept. Let's say we have g of x equals 7x. We want to find g inverse of negative 49. What's our equation? Take a moment to set it up. We set g of x equal to negative 49, which gives us the equation 7x equals negative 49. Dividing both sides by 7, we get x equals negative 7. So g inverse of negative 49 is negative 7. As you can see, the process is very straightforward. To find the value of an inverse at a point, you set the original function equal to that point and solve for the input. We've talked about inverse functions conceptually and algebraically. Now let's explore the beautiful graphical relationship between a function and its inverse. By the end of this segment, you'll be able to describe this relationship and use it to sketch the graph of an inverse function. Let's recall the core idea of an inverse. If a point AB is on the graph of f, meaning f of a equal b, then the inverse function must take b back to a. This means f minus b equals a, so the point BA must be on the graph of the inverse. So for every point AB on the original function's graph, the point BA is on the inverse function's graph. We are simply swapping the x and y coordinates. So what does this swapping of coordinates look like geometrically? It's a reflection. This is the key graphical insight. The graph of an inverse function is a mirror image of the original function's graph, where the mirror is the diagonal line y equals x. Look at this general example. The blue curve is our original function, f of x. The black dashed line is our mirror, y equals x. The red curve, f into our sum x, is the reflection. You can see how every point on the blue curve has a corresponding reflected point on the red curve. Let's use this principle to solve a problem. Here we are given the graph of a function, and our task is to sketch its inverse. The first step is to draw our line of reflection. Let's add the line y equals x to our graph. This will be our guide for the reflection. The next step is to identify a few key points on the original blue curve and find their reflected coordinates. The graph clearly passes through 3 main points: the start point at negative pi over 2, negative 1, the origin at 0, 0, and the endpoint at pi over 2, 1. Now, to find the points for our inverse function, we just swap the x and y coordinates for each of these. So minus pi over 2 minus 1 becomes minus 1 minus pi over 2. The point 0, 0 stays at 0, 0 because it's on the line of reflection, and pi over 2, 1 becomes 1. Now we plot these new points on our graph. Here's the point, minus 1 minus pi over 2, here is 0, 0, and here is 1, 2. The final step is to connect these points with a smooth curve, making sure it looks like a reflection of the original curve across the line y equals x. And there we have it. The red curve is the graph of the inverse function. It's a perfect mirror image of the blue curve across the line y equals x. So we've learned that the graph of an inverse function is a reflection of the original function in the line y equals x. And we can use this property to accurately sketch the inverse. To wrap up our introduction to functions, let's briefly touch on a very important application: using functions as mathematical models. In the real world, we often want to describe and predict processes. Functions are the primary tool we use to create mathematical models of these processes. A model is essentially a function that attempts to describe the relationship between two or more variables. For example, Zipf's law uses a function to relate a city's population to its size rank. However, it's crucial to understand that real-world data is messy. Models are almost never perfect. Let's consider this example. A model for the population of pigeons, P, on an island T years after being introduced is given by P of T equals 100T squared. This is a simple quadratic function. But is it a good model? Let's think critically about its limitations. First, what happens at the start, at time t equals 0? The model gives P of 0 equals 0. This says there were no pigeons at the start, but the problem states pigeons were introduced to the island. This is a logical inconsistency. What about fractional time? Let's say after 4 months, which is 1/3 of a year. The model predicts about 11.11 pigeons. This is nonsensical in reality. You can't have a fraction of an animal. The model gives non-integer values, which is a flaw. What happens as time goes on, say after many years? The quadratic function grows forever. It predicts the pigeon population will increase to infinity. This is biologically impossible. Eventually, the island would run out of food, water, or space. Finally, does the real world operate so smoothly? The model is perfectly predictable. It doesn't allow for random events like disease or seasonal changes in birth rates. Real populations fluctuate. So, does this mean the model is useless? Not at all. It might give a reasonable approximation for the first few years. The key takeaway is that when we use functions to model the real world, we must always be aware of their limitations and the context in which they are applied. That brings us to the end of our lesson on the concept of functions. We've covered what a function is, how to use function notation, the difference between one-to-one and many-to-one, how to find domain and range, and the concept of inverse functions, both algebraically and graphically. These are foundational ideas that we will build upon throughout the course. Thank you.